Hello everyone. As in the last lecture we left the discussion over the properties of metal and metal in the electrostatics, which we are taking here. Okay, so let me have the basic discussion over the metals in the electrostatics. Okay, so in this case when electrostatics you are dealing with, the net field inside the material must be zero. What does it mean? It does mean that when the metals are placed in the external field, the polarization take place. In the case of capacitors, we will be discussing about the polarization, but till then you take an idea what actually the polarization is. Whenever any body is placed in the electric field, suppose the electric field is in this direction and you are taking a metal which is placed in this, okay, what happens? There are the charged particles in the metals, the free charge carriers are there, but these free charge carriers are, in a very random manner. This electric field will, the polarization will take place, and the polarization does mean due to this electric field, polarization will take place, and in that polarization the separation of the negative and the positive charges will take place. That does mean if this is a body, if this my hand I'm taking as a body which is placed in the electric field, it does mean the polarization, actually what happens in the polarization, the negative charges and the positive charges are getting separated. Okay, so negative charges will be in this direction, suppose like this. So negative will be there if the external electric field is there, so positive will be there. So charge separation will take place, and this charge separation will result in induced electric field, but this induced electric field is of that amount which is of the external electric field. So the E reduced does mean, that means how much electric field is left in the metal, that means induced in the opposite direction, external outside direction. So E external minus E induced will remain 0, so that means it will be 0. So in the case of metals in the electrostatics, we will be taking the case that electric field inside the metal or the conductor is 0. Okay, then after, the charge given to a metal always appears on the surface, that is a Gauss theorem. I hope you understand the Gauss theorem. I'll be discussing that, don't worry, but till then take an idea here that what actually the Gauss theorem is. Gauss theorem says the electric flux through a closed surface is the 1 by epsilon naught times the charge enclosed in that surface, that is E dot ds q by epsilon naught. You represent it like this. Okay guys, so now EDS is q by epsilon naught, and you know that charge given to a metal always appears on the surface. Why it is so? That means flux is 0, the flux is 0 inside the metal. Why? Because electric field is 0. आपने first point में बोला electric field inside the metal is 0. When you put the E there, that means E will be 0. E will be 0 means phi is 0, sorry. So phi will be 0 when E is 0. Electric flux does mean the magnetic field lines passing through any particular surface which you are taking, that is coming out to be 0. And when electric field lines are not there, that means charge is not there. And this is somewhere known as the skin effect, that whenever you talk about the metals, the charge never reside inside the conductor, inside the metal, it comes out on the surface. So this is explained by the Gauss theorem. Okay, and the electric field is always perpendicular to the surface which you are taking. The tangential component of the electric field over the surface is always 0, but it is taken as perpendicular, like this direction is of this one, the perpendicular direction over the surface. And you studied that E is 0 inside the metal, but the relation between the potential and the electric field is the negative gradient E minus dV by dr. Okay, so E equals to minus dV by dr. E 0, which expression has differentiation 0, which has the differentiation of constant quantity. That does mean that the potential is constant inside the metals. Okay, so just outside the metal, field is always perpendicular to its local surface, which I have told you that. I have written here. This is the third point. So three properties are there. Three properties I have discussed now till now. That is, inside the metal you take the electric field 0 just because of the polarization. Induced electric field inside the metal is in such a way that it is equal in magnitude with the external electric field, and there will be no electric field left inside the metal. So that's why we take E equals to 0 inside the metal. And the second point is we discussed the Gauss theorem. The Gauss theorem is किसी भी कंडक्टर में, किसी भी आप सरफेस में जितना चार्ज इनक्लोज्ड होता है उसका 1/ε0 टाइम्स करेंगे तो वो मैग्नेटिक फ्लक्स आ जाता है, एंड मैथमेटिकली इट इज डिफाइंड एज इलेक्ट्रिक फील्ड इनटू एरिया वेक्टर. ओके, डॉट प्रोडक्ट ऑफ द इलेक्ट्रिक फील्ड एंड एरिया वेक्टर. Don't worry, we will be discussing that. Okay, so these three properties, and then I have drawn the diagram here to let you understand. If this is negative charge density on the surface, it is in the this arrow will be shown there, and when positive is there, it is away from the surface, but it will be perpendicular there. And then next point, it is very important. Suppose I have taken a cavity without charge. The cavity, inside the cavity, you see the cavity is there, and the cavity is not having the charge inside it. And you know that in the case of conductor, the charge comes out on the surface. The whole charge comes out on the surface, and the charge I have represented here. If I take the 3 points here, E, A, B and C, and ask you what is the electric field here, definitely you will be saying that, sir, electric field is 0 inside the metals, and even there is no charge. Okay, so EA, EB, EC will be 0. So that is the case of cavity without charge. Okay, these are the concepts, friends. Okay, so if you are having the knowledge of these basic concepts, numericals are nothing to you. Okay, you practice any type of book. I will be sharing a series of H.C. Verma, complete H.C. Verma, don't worry. Okay, but there is a time problem with me. I will be discussing the complete solution of H.C. Verma chapter wise, and 10 to 12 question in each chapter, in each video. Okay, so till then, please make the fundamental inside you, inside your mind, that what actually the concepts are. Without any concepts, you cannot do the physics. Okay, so now the cavity is now having the charge Q1. If this cavity is having the charge Q1, that does mean if the point A is there, this point A, suppose this point A is r distance away from the charge which is kept at the center, and you are taking the whole distribution of the charge as a point charge, that means the charge distribution is having the electric field kq by r square. So now k1 is the charge, and electric field will be not equal to 0, it will be from k, that is kq1 by r square. But when I talk about EB, there is no charge distribution, there is no electric field. Okay, so that means E will be 0 there, but EC, this EC, C point is outside now from the conductor, and definitely it is placed in the field of the complete charge distribution. That means it is also having electric field here. Suppose the Q1 which is taken here, and this Q1 will be distributed over the charge, you will take this kq1 by r square. I have represented with same r, and this r is in general representing the distance of the test point. That means जहां आपको इलेक्ट्रिक फील्ड निकालनी है उसका डिस्टेंस. ओके, so as this was about electric, I discussed about electric dipole, then properties of metals are there, and some basic points and some important points I also mentioned here. Now let me explain you a very beautiful concept, and let me start with this electric flux. Okay, this is module number 2, and we are discussing the following classes in this way. Okay, so electric flux, let me give you a small recap. अभी तक मैंने क्या करवाया है. मॉड्यूल 2 में मैंने इलेक्ट्रिक फील्ड डिस्कस किया. इलेक्ट्रिक फील्ड डिस्कस करने के बाद उसके कुछ कॉन्सेप्ट्स थे जो हमने डिस्कस किए. देन आई स्विच टू इलेक्ट्रिक डाइपोल, एंड देयर आर 2-3 videos which I have posted that are revolving around electric dipole and the complete concept of electric dipole. Now electric flux is there, the third part, you can say. In the module 2, you please have the partition in this way. The part number 1 about the electric field, then electric dipole is there, and then electric flux is there. In this way the whole electric field is completed, and then after the module number 3 will be started, and that will be electrostatic potential, and that is very fundamental concept which you must have in your mind for doing numerical problems. Okay, and the whole numerical problems will be revolving around that concept. Clear? And then after, the module number 4 will be there for the electrostatics. In that we will be discussing regarding the capacitors. Okay, and you know, the capacitor is carrying more marks for your exam. Okay, so let me come back to the topic after this outline. Electric flux. Electric flux, you know, I have told you that how many electric field lines, suppose if I say the charge distribution is there, and this is placed in this charge distribution, or this surface is placed in a electric field. Okay, and electric field geometrically is represented by the electric field lines. So if I am taking this this surface, and you know, when you are asked with how many electric field lines are passing through the surface, okay, how many electric field lines are passing through the surface, that is known as electric flux. And in very simple language, it is said, it is written before you, you can put the notes in your notebook, that it is a scalar effect of the electric field. Okay, that means electric field lines, how many electric field lines are passing. And I have mentioned a word here, that is imaginary surface here. Imaginary surface here. That imaginary surface will be taken as a very important point in the case of Gauss theorem. Okay, and how mathematically it is defined? This is a scalar effect. So that means it will be represented by electric field dot product with area vector. Now this is very strange that I am pronunciating area as a vector. Area vector. Okay, area is although a scalar quantity, but in some cases when you are representing the direction in reference to that surface whose area you are considering, you take that area vector. So don't consider that area is a vector. Please, I repeat my point, that whenever there is a reference of that surface for the direction of any quantity which is a vector, in that case you take the area as a vector quantity. Okay, and which is always, this area vector is always represented by the direction which is perpendicular to that surface. Okay, like this. This is total number of field lines. This is electric flux. It is represented by phi E. Okay, and this is area vector which is represented perpendicular to the surface. For example, if I take the surface, my hand as a surface, then this direction will be the direction of area vector. If I say that the force is the surface is like this, then the direction will be that perpendicular, or it can be downward direction. Okay, so this will be the negative direction of area vector, the negative vector of the area vector. Clear? I hope I made my point clear. And this electric flux, which is a scalar effect of the electric field, you know that when you talk about scalar effect of the electric field, it means आप बहुत आसानी से इलेक्ट्रिक फील्ड को एस्टिमेट कर सकते हैं विद द हेल्प ऑफ इलेक्ट्रिक फ्लक्स. ओके, आप खुद सोचिए, आप किसी भी सरफेस पे अगर आप स्ट्रेंथ देख रहे हो और आपको ये पता हो कि वहाँ से कितनी इलेक्ट्रिक फील्ड लाइंस पास हो रही हैं, दीज आर ऑल्सो इमेजिनरी लाइंस बट गिविंग यू द आंसर. ओके, तो कितनी इलेक्ट्रिक फील्ड लाइंस पास हो रही हैं, तो वो आप क्या बताएंगे कि वहाँ क्या स्ट्रेंथ है इलेक्ट्रिक फील्ड की. सो विद द हेल्प ऑफ फ्लक्स इट इज़ वेरी इजी टू कैलकुलेट इलेक्ट्रिक फील्ड. ओके, let me switch to the concepts here, that is phi is E dot ds. ds is a area vector I have mentioned here. Let me take this. ds is a area vector. Okay, this is area vector, and this area vector is having the direction always perpendicular to the surface whose area you are considering. Okay, so this is a scalar. When you talk about the unit, that does mean electric field is having Newton per coulomb, area is in meter square, and when you put the value of electric field in terms of volt and meter, that means dV by dr, volt per meter into meter square, it will remain as volt meter. So electric flux is having unit as volt meter. Always remember there is a imaginary surface which you will be taking and about which on which you will be calculating the electric flux. Whenever there is a closed surface, area vector is always taken as outward directions. Like when there is a cube, that is ds vector, ds vector, ds vector, ds vector, does mean they are area vector which are perpendicular to the surface. So इस surface के perpendicular ये perpendicular है like this, okay, वहाँ ये है, ऊपर ये है, नीचे ये है, ठीक है. So अच्छा स्फीयर ले लेंगे तो भी आप इस पे perpendicular दिखाएंगे. तो यहाँ लिखा है मैंने, for closed surface it is always outward. Clear? Now when there is a non-uniform electric field, what happens? In that case, for the closed surface, when there is a non-uniform electric field, it means electric field lines are not uniformly distributed, so it is not easy to calculate how many electric field lines are there in a particular area. Fine. So in that case, when you put the formula phi dot E dot ds, you have to have the integration over the closed surface on the whole surface. I have represented here that suppose in this part, in this part, in this part, आपको इन सारों को इंटीग्रेट करना पड़ेगा, तब आपके पास फ्लक्स आएगा. इंटीग्रेशन डज मीन सिंपली आप एडिंग कर रहे हैं एक तरीके से, ठीक है, और फ्लक्स एक स्केलर क्वांटिटी है, इट मीन्स इट कैन बी एडेड डायरेक्टली. देन फॉर द होल क्लोज सरफेस द फ्लक्स विल बी गिवन एज इंटीग्रेशन ऑफ द फ्लक्स over the closed surface, and this integration with this sign is meaning has the closed surface, for the closed surface. Okay, okay, fine. Now I have taken example here. You please do this example yourself. Please try in this in the next lecture. I'll be discussing this first, and then we'll be marching forward through the module 2, okay, and we'll be going through the Gauss law and its application. Thank you very much.